Welcome to this video example of Newton's second law. So here's the situation in this video example. A dock worker applies a constant horizontal force of 78 newtons to a block of ice on a smooth horizontal floor. The friction force is negligible. The block starts from rest and moves 12 meters in the first 6 seconds. And the question is, what is the mass of the block of ice? Alright, to do this, let's go ahead and record first the goal of the problem. And that goal is, of course, what is the mass of the ice block? Step 2 is to visualize the problem. So we're going to draw a force diagram, also known as a free body diagram. So here's the block resting on the floor. We know that the dock worker is going to apply a force of 78 newtons to this block of ice. We also know that there is a downward force on the block of ice due to gravity. So this is the force of gravity. And we know that there is a normal force pointing upward. Since the block is not sinking into the floor nor flying up into the air, we know that the normal force and the force of gravity are equal and opposite. They balance each other. In other words, the sum of these two is 0. Let me add in the point 0 here, just to be more exact. Okay, and also recall that they said that the floor has no friction or negligible friction. So we do not need to worry about a friction force here. Okay, so now step 3. Let's see what the problem gives us as far as information. We already have the force here being applied to the block of ice. We were also told that it starts from rest, so we know that the initial velocity is 0. We know, if we look back here, that the block moves 12 meters in 6 seconds. So let's record that as well. In other words, the displacement of the box is 12 meters at a time of 6 seconds. Okay, so that's the information from the problem. Let's use step 4 to find an equation that can be helpful to us. In this case, we have a time and we have a displacement, and we're looking ultimately for mass. Recall that from Newton's second law, the sum of all forces on an object must be equal to the mass times the acceleration. So whatever the acceleration of the block in the horizontal direction, in this case to the right, that acceleration must be equal to the net force in that direction divided by the mass. In other words, if we rewrite this, we should see that A is equal to the sum of all forces divided by the mass. Or, if we rewrite the equation again, we can see that the mass, which is really what we want, if we look at the very first step up here, the mass is equal to the sum of all forces divided by the acceleration. Now, the sum of all forces in the horizontal direction is simply the force that the dock worker is using, because there are no other horizontal forces involved here. The other two forces are vertical, and we already know that they are equal and opposite, so they already balance each other out to 0. So we don't need to take them into account in this problem. So we know that this must be 78.0 newtons. So the question then becomes, well, we need to know what the acceleration is. To find that out, we can go back to our motion equations from the previous week. We know that the total displacement of something that starts from rest and is accelerating at a constant rate is simply equal to 1/2 at squared. In other words, both v0 and x0 are 0, so their terms do not appear here. That means that we can plug in these values here for this equation to solve for a. So if we rewrite this in terms of a, we get that it's equal to the total displacement of the object divided by 1/2 t squared. That means we can plug in the 12 here and divide by 1/2 times 6 seconds squared. If we actually put that into a calculator and solve for it, we'll get 0.667 meters per second squared using 3 significant figures. Now we can plug this into the A here, and we'll find what we ultimately want, the mass of the ice block, using Newton's second law. That gives us 78.0 divided by 0.667, and that comes to, again, to 3 significant figures, 117 for the mass. And remember that the standard unit of mass is the kilograms. So that's what we put in for our units. Okay. As for step 5, checking our answer, well, we do know that as long as we have newtons here and we divide by an acceleration here, we should get the standard units of kilograms. Let me be more specific here. The A units are meters per second squared. That's better. Okay. So the units seem okay. Also, we note that this 117 kilograms doesn't seem incredibly small or incredibly huge. Just to give you some kind of basis of comparison, a human being has a mass, an average mass or a typical mass of maybe somewhere around 70 kilograms. So this block weighs a little bit more than a person. So that it's not too huge. The person should be able to push this block, especially along a slippery floor, without too much trouble. In other words, we didn't get an answer of, say, 1,000,000 kilograms. That would be probably much too big for a person to create any kind of significant acceleration with. Neither is the block, say, 0.001 kilograms, in which case that would be kind of strange for a large block of ice to weigh so little. So the ballpark, looking at the general value ballpark of this ice block, it seems to be pretty decent. So there's no red flags that have popped up here. So that concludes our quick little check in step 5 of our answer. So this concludes this particular video example. Thank you for your attention.